right now. So it's done. And I will share my screen just to begin, and then I'll appoint you moderator. Let me just do this. Okay. Okay. So welcome once again to all of you. And so you saw yesterday this little flyer, so I'm not going to repeat anything, but you will notice that there is one additional piece of information that was not present yesterday on this flyer for those who have an eye for detail. And that is right here. You see this YouTube link. It is, I mean, you have it because in one of the emails that I sent you, participants, it is included. And if you click on the video tab on that, once you connect to YouTube, then you'll see that we posted yesterday's lecture already. And I'll do the same after Antoine's lecture. So we'll have 2 days worth of recordings. And that was the information I wanted to give you. So now I'm going to stop sharing my screen, and I'm going to appoint Daryl. Okay, moderator.
Good. All right. Well, welcome. Good afternoon, everybody. Welcome back to part 2 of Professor Antoine Georges' lecture. And today's lecture will be about 75 minutes plus another 45 minutes of questions. So if you do have a question, during his lecture, please use the chat feature. And then at the end of the lecture, I'll read through the chat list of questions and then call on people who want to ask additional questions in our ample time at the end of the lecture. Just to remind you, Professor Georges has a dual position at the Collège de France, as well as the Flatiron Institute in the Simons Foundation in New York City. Please, Antoine.
Thank you. So I suppose what I need to do now is share my screen, right? So let me try that. And if I start the presentation, you hopefully will be able to see my slides. Let's see.
Yes, yes, very good.
Is this working? Okay, can you see my mouse as well?
Yes, to the mouse and the slides.
Okay, wonderful. Okay, so this is the second lecture of this series of 2. And just to remind you where we left things yesterday. So for about 30 minutes or so, I presented some sort of broadband introduction to the collective phenomena that are hosted by transition metal oxides and the new methods that are currently available to control these functionalities, in particular by growing materials in an atomically controlled manner. And so that was kind of an introduction to the field. And then I went on introducing some basic notions about the structure and electronic structure of these materials. I covered sort of the perovskite crystal structure mostly and its distortions, crystal field theory, and we stopped at the point where I was going to move from crystal field theory all the way to band structure and electronic structure. So this is what I would like to do today, is focus on the electronic structure of these materials, and then gradually turn on interactions and talk about the physics of strong correlations in these systems. Okay, so in order to introduce some basic notions about band structure of such materials, I would like to take a specific example. because that will make things more concrete. So yesterday, you probably remembered we talked about the perovskite structure, and we saw that many of the oxides actually have significant distortions as compared to the ideal cubic case. But here, for simplicity, to start with, I would like to focus on one material, which is indeed cubic in nature, in reality. And this is strontium VO3. So this is a cartoon of a drawing of the crystal structure of strontium VO3. And you recognize this corner sharing octahedra that form a perfectly cubic lattice in that case, with the vanadium at the center of the octahedra. The oxygens are the blue balls, and because this is cubic and it has no distortions, the bonds are perfectly straight at 90 degrees one from the other, and the oxygen metal oxygen band is perfectly 180 degree. Okay, so that's a very simple crystal structure, and this material is also, by the way, from its physical point of view, for a rather simple material. It's a metal, and it has, I would say, a moderate degree of correlation effects if one judges from the ratio, for example, of this measured specific heat coefficient to what would be predicted by band structure calculations. The enhancement, which is measured versus band structure, is about a factor of 2 or 2.2, something like this. So we can also talk about an effective mass enhancement of about 2 to 2.5. So it's a moderately correlated metal. Okay, so what we learned yesterday is that if you just do simple crystal field theory based on the electrostatics between the metal and the oxygen for the vanadium at the center of its oxygen octahedra, because of the cubic symmetry, we would expect a splitting of the d orbitals, the 5-fold degenerate d orbital, into a lower lying T2G triplet and a higher lying EG doublet. And this, of course, should reflect in turn in the full band structure of this material. So what you see here is a plot of the Bloch bands, so the value of the energy levels when you do a state-of-the-art electronic structure calculation following a certain path in the Brillouin zone. Of course, here we have a 3-dimensional Brillouin zone. So this is a certain path which connects high symmetry points in the Brillouin zone. So for example, here is the gamma point, which is written G here at the center of the zone, as is conventional. And then going from gamma to X means moving like this in the AB plane. Moving from gamma to R means moving here along the diagonal. Okay. And if you look at the gamma point, which is the high symmetry point, you will observe that, so the Fermi level is here conventionally positioned at 0, and it's indicated by this horizontal blue line. And obviously, because just for nominal valence counting, strontium is 2+, oxygen in that case is definitely a good 2-. We don't expect too many ligand holes in this material. So vanadium should be 4+. Vanadium 4+ corresponds to 1 electron in the D shell. So we expect that the Fermi level crosses a bunch of bands with basically D character. And indeed, if you look around the Fermi level, you see that there is a set of bands here that cross Fermi level. And if you count the number of bands, so you should count them away from a high symmetry point, because at the high symmetry point there are extra degeneracies. So for example, if you count here, you see 1, 2, 3 bands. And these 3 bands are the bands that originate from the T2G levels of the crystal field theory. So obviously each atom in its octahedral cage has 3 perfectly degenerate T2G level, but as we build the crystal out of this octahedral cage, there is hopping between sites, and that creates a band, which is a linear combination of all these T2G levels. And as a result, this is the dispersing band, and you count 3 of them. So you should understand that these bands result from the hybridization of on-site atomic d orbital forming the T2G triplet dxy, dyz, dxz, which are hybridizing with the p orbital on the oxygen. And as we saw yesterday, because the T2G orbitals point away from the oxygens, this hybridization, which allows hopping, is mostly pi bonding, while the EGs would be sigma bonding. Okay, so you see that understanding the local atomic physics of these materials, namely the atom into its octahedral cage and how orbitals bind with each other, which is sort of the chemist way of thinking about solids, is extremely helpful in making sense of this plate of spaghetti here, which otherwise can appear a little bit like, you know, coming out of a black box. But you can reconcile chemical intuition with this band structure calculation by thinking in terms of atomic orbitals and how they split and how they overlap between one side and the other. Okay, so we have our 3 bands which derive from the T2G states. And indeed, if you now look at a high symmetry point like gamma, you see that these 3 bands are exactly degenerate at that point, as you would expect from cubic symmetry. And by the same token, if you look a little bit above Fermi level, you have a set of bands, 1 and 2, which are empty and do not contain electrons, which again are degenerate at the gamma point. And obviously, this is the vanadium EG band. So at least you can guess this must be the vanadium EG band. So again, these are, I call them vanadium bands, but they actually result from the hybridization between the vanadium d x square minus y square and z square orbitals, which this time sigma bond with the oxygen orbitals. And this will create, you know, bands that are anti-bonding and bands that are bonding. And those ones are the anti-bonding bands resulting from the hybridization between the oxygen orbitals and the vanadium orbitals. Okay, so these 5 bands are derived from our vanadium state, split by the crystal field splitting. And you know, we could evaluate this crystal field splitting by taking the center of gravity of this T2G, which would be here somewhere around 0, and the center of gravity of these 2 bands, which would be, I don't know, somewhere here, okay? And you could read off from these plots that the typical value of that crystal field splitting is something like maybe 2 to 3 eV. Okay, so it's a rather sizable number. It's a number which is actually somewhat larger than the bandwidth of this set of T2G bands itself, which, you know, I didn't make a careful measurement here, but goes from about -1 eV to something like maybe a little less than maybe around 1.7 eV or so above Fermi level. So the overall bandwidth here is something like 2.7 or 2.8 eV. Okay. So we understood this group of 5 bands. Now we also have to understand this group of spaghettis here. And again, if you count these bands away from a high symmetry point and you have a good eye, you will count that here there are 9 bands. And the 9 bands are easy to understand. They result from the hybridization between oxygens and the vanadium, but they are mostly oxygen bands, this time forming bonding combinations with the vanadium. And because we have 3 oxygens per formula unit, and one formula unit per unit cell in this simple cubic structure, we expect 3 p orbitals for each oxygen times 3, which is 9. And this is indeed our 9 bands of dominant oxygen character. And then there are also a bunch here of bands way above Fermi level that will not play a very important role in understanding this material. And if you really want to interpret them, you have to think about empty states of these various atoms. It turns out these guys are mostly strontium 5s and 4d bands. So you see how by properly understanding bonding and crystal field splitting and so on, and symmetries, using more chemistry language, you can bridge the gap with electronic structure calculations, which are of course done using density functional theory in various approximations, and make sense, physical sense of what you see here on that plot. Okay, correspondingly, these are the spaghettis or the bands, but we can also turn this into a plot for the density of states. And you see that there is a bunch of states here that are somewhere between minus 1.7 eV and plus 1 point something eV. And these are the dominantly vanadium bands, okay? These are the T2G bands with a very characteristic shape of the density of states, which contains, by the way, a very sharp peak here at about 1 eV above Fermi level. This peak originates from what's called a Van Hove singularity, which corresponds to a flat region of the band. Actually, this one here, you see there is a region which is flat, which is actually a Van Hove singularity, which leads to this very characteristic T2G peak in the density of states, which is often, I mean, always seen in sort of T2G bands. And correspondingly, these are the vanadium EG bands, and these are the dominantly oxygen bands. So if you look at this plot, what you will see is that the total density of states, which is depicted in black, has been decomposed into blue, red, and green partial densities of states, which are labeled according to the character of a given atom. So blue denotes a component of the density of state, which is mostly oxygen. This denotes vanadium T2G, this denotes vanadium EG. So how do we actually decompose a given state into its various orbital components? So this is a useful tool which allows to better bridge the gap to chemical intuition, and this is called a fat band representation. And I want to introduce this notion because it's very useful in practice to understand the electronic structure of these materials. It's also something which is more or less systematically proposed in electronic structure codes that you may want to use at some point and helps understand a given material. So the fat band representation is based on a very simple concept. At a given K point in the Brillouin zone, and for a given band nu here is a band index, you calculate the Bloch wave function, which of course is something like a modulated plane wave, psi k nu, and you look at the overlap of that wave function with a given localized atomic-like wave function. So it could be just the wave functions of just the isolated atom, or it could be some more sophisticated object like a Wanniers function with a certain orbital character. That's basically your call. But here you see that this wave function is labeled by, well, what you expect from an atomic wave function, namely the angular momentum L and M, which is Lz. So L would be 2, for example, for D state. And you look at this overlap and you take the square of this matrix element, And that tells you how much of the block wave function is built out of an atomic orbital of a certain type. Because you can, of course, use the atomic orbitals as basis sets, and you can expand your wave function on the atomic orbitals on each site. And so this tells you about the nature, what, if you want, what are the inner components of the block wave function. So if you do that, you can make plots like this, in which the same set of spaghettis I had before is now labeled, is now decorated with a symbol which has a width proportional to the value of these matrix elements. So for example, if you look here, this is using for phi LM the, say, some Wannier function or some cubic harmonics of the cubic atomic wave functions of the T2G set of atomic states. And you see that those set of states have only a tiny component, a tiny matrix element of that type, while those set of states have a big matrix element of that type. And so this very clearly demonstrates that indeed the states that are here are vanadium states of T2G nature, and with that equal to these states of the vanadium with T2G nature. So this is a very useful representation, and the same way that you can paint the bands in this way, you can do the same thing for the density of states, and this is what was done there. So in this manner, you can decompose the density of states into its various orbital components. So this is done here for the vanadium T2G. And of course, you see that the states down there that we called oxygen before have, of course, a certain amount of vanadium component. And that's not surprising because they are bonding combinations of vanadium and oxygen in the same way that those guys are antibonding combinations of vanadium and oxygen. So you can repeat this exercise for phi LMs that corresponds to oxygen states, and you will discover that by and large, the oxygen character is bigger here, and this is indeed the set of 9 bands that we identified as oxygen bands. But of course, the antibonding set of states here also have some oxygen character because they hybridize. And you can repeat this exercise for phi LMs that have vanadium character, but with EG symmetry. And you find indeed that the 2 bands that we guessed were vanadium EG bands are the ones that I mean, this analysis supports this interpretation. Okay, so at that point, you have a set of tools in your hands which are based on band structure theory and as implemented in a sort of state-of-the-art DFT-based codes that you can use and download from the internet. And with these techniques of projection onto atomic orbitals allow you to make contact with chemical intuition and bonding between atomic orbitals, which is more the language of the chemist. And doing this bridge between the 2 languages is actually very, very useful in practice. So coming back to this material here, what are the key things that we learned from a physics point of view by looking at this band structure? Well, we learned that the active states near the Fermi level are the T2G manifold of 3 bands, and that this manifold is well separated from a set of 9 oxygen bands and 2 EG bands below and above Fermi level. We learned that the T2G bands are occupied by 1 electron in total, as requested by the naive charge counting. And indeed, if you integrate this density of states, this black stuff up to 0 here, you will find 1 electron. We learned that the T2G bandwidth of the set of 3 states is about 2.6 eV, and that there is substantial splitting between the oxygen and the rest of the band. If you actually look at the center of gravity of these oxygen bands and those T2G bands, you will find that the distance between these two set of bands is about 6 eV. And so this means that the oxygen states are really well below the vanadium states, which means that the charge transfer energy in the jargon of the field, which is the energy it takes to actually transfer charge from one side to the other, is a large energy when it comes to transfer between oxygen and these states. What you also learn is that obviously the density functional theory calculation in this approximation is giving you a metallic state. You see that the Fermi level is in the middle of a set of occupiers, not quite in the middle, just 1/3 occupancy, but somewhere in the middle of a set of occupied bands. So this is definitely a metal from a density functional calculation point of view. And obviously, this calculation is not perfect as compared to nature, because if we calculate the effective mass just by looking at the density of states and compare it to the effective mass measured by specific heat in an actual experiment, as I mentioned before, we find that the DFT calculation in the LDA approximation roughly underestimates by a factor of 2 the experimental effective mass. So this points at the fact that there are some electronic correlations that are not included properly in the band structure calculation, but that this discrepancy is more a quantitative discrepancy than a qualitative discrepancy, in the sense that the calculation correctly predicts that the system is a metal. Okay, so this is a point that I sort of made before, which is that the hopping is mostly via oxygen, hence this notion of bonding and anti-bonding bands, whereby when you form linear combinations between vanadium and oxygen orbitals. So you should really think of the thing that generates the bandwidth of this material, not as a direct DD hopping, which is very small because of the cage effect, but as something that goes through oxygen. So the effective DD hopping will be something, just using second order perturbation theory, like the square of a matrix element between P and D states, there is direct overlap there, divided by an energy difference between oxygen and D states, which is the charge transfer energy we talked about before. So this is in particular why in oxides, the typical bandwidth that we are talking about are often quite small here, just a couple of electron volts, because of this indirect hopping through oxygens. Okay, so everything is nice and good. And now I would like to raise a puzzle which is related not to strontium VO3, but to a bunch of other materials that are close cousins of strontium VO3, just to wake you up and have a little bit of a physics question in front of you. So this strontium VO3 material is just one of a broader family of materials. And here are 4 members of this family. 2 are vanadates and 2 are titanates. So you could say, well, why am I saying that these are members of a similar family? Because after all, they are different and they involve different atoms. Well, I claim they are members of a similar family for 2 reasons. The first one is that vanadium and titanium are next to one another in the periodic table, if you remember yesterday's lecture. And the other one is that these 2 materials have a divalent rare A cation, which is strontium and calcium. So that means vanadium 4+, which means 1 electron in the D shell. While those 2 titanates have rare earth, which is trivalent, which is lanthanum 3+ and yttrium 3+, leading to titanium in the 3+ configuration, which is also D1. Okay, So basically, we have two atoms that are next to one another in the periodic table, and and the occupancy of the D shell is the same in each case. So these set of materials are indeed cousins or members of a similar family. And at least from this point of view, they also have a similar crystal structure, although, and I'll come back to that, this is very important, this guy is strictly cubic, but those ones have some of the distortions that I mentioned yesterday. Now here is the puzzle. These two materials are metals, and I already described a bit the mass enhancement of this one. This one has a slightly larger mass enhancement by about 3.5 instead of 2.5 in that case. But those two here are insulators. And lanthanum TiO3 is a small gap insulator. I mean, the gap being small is not so easy to precisely extract from optics, but it's something like 0.2 eV. This guy has a much larger gap of about 1 electron volt. And so the question is, why, although these materials are very similar, why are two of them metals while the two others are insulators? And on top of that, there are magnetic insulators at low enough temperature. This guy turns out to be a non-ferromagnet with an AL temperature off the top of my head, I think it's about 130 Kelvin. And this guy is actually a ferromagnet, curiously enough, with a Curie temperature of about 30 Kelvin, so much lower. So these four cousins are actually very different kind of animals, and the question is why? Okay, so to understand why, we have to ask for, they are not identical, they have some differences. From this local electronic structure point of view, they look somewhat similar, but their crystal structure is actually somewhat different. And we can repeat the sort of electronic structure, band structure calculation that I mentioned before, and for each of these materials, and also look at their crystal structure. And if you do that, what you will see is that strontium VO3 is purely cubic, but calcium VO3 is distorted as compared to the cubic structure. It has tilts and rotation, leading to an orthorhombic crystal structure with 4 formula units per unit cell, like depicted here. And lanthanum TiO3 is a little bit more distorted, and yttrium TiO3 is even more distorted. So as we go from left to right here, we start from cubic, and we have an increasing degree of distortion. And obviously, as you could immediately guess, these distortions mean that the metal-oxygen-metal adjacent, metal bond is not purely straight anymore, in contrast to strontium VO3. And this is, in all likelihood, going to reduce the TPD that I had before, the hopping between oxygen and metal, and hence reduce the bandwidth. And indeed, if you do an electronic structure calculation, this is what you see. You see that the bandwidth is gradually reduced. And if we collect that, and you can see this here as well, that the bandwidth here is broader than the bandwidth here. And if we collect this in a little table, you will see that the bandwidth of this triplet of T2G-like bands is about 2.8 eV for strontium VO3, and it's down to 2 eV for yttrium TiO3. So if you are a simple-minded theorist who basically only knows the Hubbard model, you will give a sort of spherical cow answer to the question I asked before, which is, well, this is very simple. The bandwidth is reduced by about 30%. So this, by reducing the bandwidth, we managed to bring this material across the transition to a multi-insulator. And so this is a bandwidth sort of controlled mod transition. Just happens that the bandwidth is smaller than the critical value to reach the mod state for those two materials, lanthanum and yttrium, while it is larger for the strontium and calcium materials. Okay, so the question is this all there is to it? And to answer this question, we need to do a better job taking into account the strong interactions between electrons, which are not fully taken into account in the DFT-based calculation. And we also need to take into account the structural differences between this material. And as you will see in the coming slides, the answer to the question that was raised before is this is absolutely not all there is to it. And actually the bandwidth effect may not even be the biggest player in that game. So this is a little bit of a warning against simple-minded theory that knows only hopping and U, okay? I don't mean U, I mean Hubbard U, okay? And describes everything by a Hubbard model. In fact, the really key player here is not so much the bandwidth, of course that plays a role, but it is the splitting between G2G state that is induced by the distortion, which is by far a very important player in the, if not the dominant player in that thing. So when you reflect a bit more about it in view of my lecture 1, you will realize that the distortion has two effects really. It has this effect of reducing the total bandwidth that we just discussed. But coming back to our crystal field description, it also has the effect of splitting the T2G orbitals. And if you look carefully into these complicated spaghettis, so of course these guys have now many more bands because the unit cell is, the unit cell is smaller, there are more bands per unit cell. But if you look carefully, you will realize that there are some small splitting between bands that reflect the effect of distortions. And if one extracts a typical energy scale for these effects by looking at center of gravities of bands again, you will see, or you can diagonalize some local density matrix to extract these numbers, you will see that the T2G bands are actually split into a set of 3 bands, which are no longer degenerate and are separated by about 0.2 eV between the lowest most and the topmost. And in the case of yttrium TiO3, this number is even 1/3 of an eV. So it is not a small number. It's actually, more than something like 15% of the bandwidth that this splitting is actually, this splitting is actually a very significant effect. Well, as I explained briefly yesterday, the criterion for having a mode transition is actually very sensitive on the degeneracy of the band, on the, whether you have a perfectly 3-fold degenerate band or whether you start splitting. And I'll explain that in more details later, but this effect is indeed very important to understand why 2 of these metals are metals and 2 are insulators. Before I get to that, however, I want to say a few more, just one more slide about more from a chemical intuition point of view, what is inducing this splitting of the T2G states? Because usually you think that T2G states are pointing away from the oxygens. So if you start tilting the octahedra, you are not changing the local electronic structure, the local structure of the octahedra. It's not like a Jahn-Teller distortion where you deform the octahedra itself. So why should that affect the T2G state so much? And the answer to that question was provided to me by Ole Andersen, with whom we did this work many, many years ago. And he realized that the T2G orbitals are not pointing to the oxygen, they are pointing 45 degrees away from the oxygen, but they are pointing to the rare earth. And it is actually the change of covalency between the metal site and the oxygen site and the rare earth, which is actually responsible for inducing the splitting within the T2G manifold. So the rare earth also plays a role in this business. Of course, from general symmetry consideration, we expect the splitting of the states because of the lifting of the cubic symmetry. But the question is, why is that so large as 1/3 of an EV? And in terms of chemical bonding, the answer to that question involves the rare earth. That's the message. Okay, so what I want to do now is actually continue understanding this puzzle. You know, why 2 of these materials are metals while 2 others are insulators. And obviously, if we do just a density functional based calculation in the non-magnetic state, all these materials come out to be metals. You see this here, this is the Fermi level, and for all of these materials, the Fermi level crosses, as you would expect, this set of partially filled D states. And from that point of view, all these materials are metallic. Of course, it's a different story if we start considering the magnetic state of this material. Lanthanum TiO3, for example, is an antiferromagnet, and this will double the unit cell and lead to the possibility of a Slater-like antiferromagnetic gap. But when you actually think of this, yttrium TiO3 is a material which has a Curie temperature of 30 Kelvin, which points at exchange constants which are of the order of several hundred Kelvin maybe, while the gap of this material is 1 electron volt. So you can very happily heat up the system above its ordering temperature, have a very, very small magnetic correlation length, and still have a very decent insulators with a gap of 1 eV. So the magnetism has absolutely nothing to do with inducing insulating behavior in this material. You could get it from a band structure point of view, perhaps, if you do the magnetic structure, but you would not have understood the correct physics, which is really the physics of strong local interactions. Okay, so we need to understand these interactions. And to understand these interactions, as I already mentioned, we need to be a little bit more realistic than just saying there is a Hubbard U which comes from the screen Coulomb interaction. So I would like to spend a little bit of time talking about interactions in these shells. Well, the first thing will be to understand what we mean by interaction. Of course, the first piece of the interaction is just indeed the screen Coulomb interaction. And I would like to consider the following process. So we have 2 neighboring atoms in which the shell is in some dn state with n electron in the d shell. So in the materials I just talked about, n is 1. And we consider the process by which we transfer 1 electron from the d shell of atom A to the d shell of atom B. And when I'm talking about d shell, of course, I'm talking about these hybridized states between oxygens and between the d states of the metal and the oxygens, say the T2G states of the previous example. So we go from dn to dn plus 1, dn minus 1. That's a neutral charge conserving process, but in which there has been a charge transfer between atoms, hence the name charge transfer. And we calculate the cost, or we think of the cost of this process. So the cost of this process is the ground state of the n plus 1 configuration plus the ground state of the n minus 1 configuration, which is the final product, minus twice the ground state of the n configuration, which is the initial thing. And you see, incidentally, that I can also write this quantity in a way that chemists like to do as the energy for ionizing, adding an electron to the system, minus the energy for removing an electron from the system. So it's often called ionization minus affinity. And this thing defines an effective interaction or an effective electrostatic cost for charge transfer. that I'm going to call U effective. And from a very qualitative point of view, you may guess the following. If this effective cost for charge transfer is much smaller than the kinetic energy you can gain by delocalizing the electrons over the whole system, you'll probably say that it's reasonable to have a metallic state. But if this energetic cost is much larger than the kinetic energy to delocalize electrons, then it's likely that the electrons just want to stay put on their atom and not move around, and that's the definition of a multi-insulator. So this is a rough criterion for deciding whether we have a metal or an insulator, and of course, this is set by this Coulomb, screen Coulomb electrostatics, while this is basically set by the hopping between electrons. So it's a competition between electrostatics, repulsion, and hopping. If you want to be a little bit more precise, you will need to address more seriously the question of what is this U effective? And this is a fairly subtle question, because at the end of the day, this will depend on which description you choose for your system. Are you going to write an effective description which contains only the T2G orbitals, a 3-band model to describe the system? Or are you going to keep in your description the full set of states, all the oxygens and T2Gs and EGs and empty states that we described before? And obviously the nature of the screening that you have to take into account in these two descriptions will be different. Hence, the value of U effective will be different. So when we talk about what is the Hubbard U for a given material, we should always have in mind that this depends on your target Hilbert space that you will retain in your description. Okay, so this slide illustrates that point, that the notion of what is U or U effective will depend on the selected energy range for the model you're going to describe. So just to be more concrete, we could have an effective model in which we decide to only consider the 3 bands near Fermi level. And in practice, this means constructing Wannier orbitals that provide a good description of these bands. These Wannier orbitals will be strongly mixed, have a strongly mixed character between vanadium and oxygen, as illustrated here. This is not a cartoon, this is an actual calculation of these Wannier orbitals. You see that they look like a D state. They have a symmetry of a D XY state, for example, here. But obviously, they have significant weight on oxygens as well. While we could take a different description in which we're going to retain all the states, T2G and EG and oxygen bands. And in that case, we can construct Wannier orbitals that look a lot more like pure atomic-like orbitals. So here is like a DXY orbital here, right? And this is a matter of choice. You could do theory taking into account all these 9 + 2 + 3 bands. Okay, so that would be a 14-band description. Or you could do a theory that takes into account only a 3-band model. And at the end of the day, if you do your theory right, you should find the same answers. But of course, provided you correctly take into account the fact that the interactions that you'll have to apply to this set of states is not going to be the same than the interactions that you have to apply for this set of states. The value of U here will be much bigger because you have more states and less screening than the value of U here that will include the screening by the states that you've not included. Okay, so the typical sort of models that you will end up with are models that either retain the full D and P states and will involve TPD hopping and charge transfer between oxygen and metal, and then a whole bunch of interactions, or it will be a low energy model including, say, only the T2G states, and this will contain a renormalized hopping, which will be of order TPD squared over delta, plus some screen Coulomb interaction, as we just discussed. Okay, so now I'm gonna tell you a little bit more about the structure of this interaction, because up to now I've just I've just said something about a U effective, but we don't have a single band Hubbard model. Even in the minimal description, we have at the minimum a 3 orbital or 3 band model. So this leaves the possibility of many more interactions than just an overall Hubbard U. And it turns out this is extremely important to understand the correlation effects in these materials. So from now on, I'm going to focus just to fix ideas. This can, of course, be generalized, but I will focus on an effective description where we just retain a 3-fold set of bands, the T2G bands near Fermi level, and in cubic symmetry, just to make our life really simple. And I will describe what are the key matrix elements of the interaction in this description. So it turns out that for a T2G triplet with cubic symmetry, there are actually only 3 independent Coulomb integrals, but you know, there's still 3. There is a U, which is the usual Hubbard U, which, as you see here, describe the interaction or the electrostatic repulsions between 2 electrons that sit in the same orbital M on the same site. So obviously, if they sit on the same site in the same orbital, they have to have anti-parallel spin because of the Pauli principle. So this is the Hubbard U in its full glory, and this is usually the biggest interaction. The one I called U effective before is really this. Then we have a U prime, which is still 2 electrons sitting on the same site, and it's also pure electrostatics, but sitting in different orbitals, for example, one in XY and one in XZ. And this matrix element is smaller than U for obvious reasons, because the overlap of these orbitals is less than the overlap of the same orbital with itself. And so U prime will typically be smaller than U. And then there is actually an additional interaction, which is an exchange interaction typical of quantum mechanics, which is not a density-density term, as you see here, and which is, as you will see a little bit later, very much related to the Hund's rule and the Hund's coupling. So we have these 3 interactions, and it turns out that when you do correctly the mathematics, the full interaction Hamiltonian, as derived by Mr. Kanamori many years ago, for a T2G shell is built of these 3 interactions, U, U prime, and then U prime minus J. So this is the cost of putting 2 electrons in same orbital with anti-parallel spin. This is the cost of putting 2 electrons in with anti-parallel spin, but in different orbitals, U prime. And this is the cost of putting 2 electrons in different orbitals with parallel spins. And this is smaller than this interaction by this exchange integral J. That just results from the usual principles of quantum mechanics. And then if you want to be really correct, this J also enters additional terms, which correspond basically to exchange processes or pair hopping processes, which cannot be expressed as a density-density interaction. So this is what you get from general considerations for a T2G shell based on cubic symmetry. And the same sort of analysis can be done much more generally for an arbitrary D shell. Details can be found, for example, in this classic book. And this is the work of Raka and Slater in the late 40s, early 50s that classified all these interactions in D shells. Incidentally, in the case of a T2G shell, this Hamiltonian can be nicely written in a compact way in terms of the charge, spin, and orbital angular momentum operators. Okay, so I just want to come back for a moment on these 3 interactions, U prime and U prime minus J. So you see that this being the smallest of all these 3 interactions is telling you that it's always more favorable from the electrostatics point of view to put 2 electrons in different orbitals with parallel spins instead of same orbital with a parallel or anti-parallel spin. And this is something that was formulated many years ago by Mr. Houches in the 20s. You're probably familiar with the Houches rules that basically guides you towards how you build the ground state of a multi-electron atom. And what Mr. Houches says is that the first thing you should do is maximize total spin, and then given total spin, maximize total angular momentum. And then, you know, there is an additional thing with spin orbit that I'm not going to detail. But this is very nicely illustrated by this Hamiltonian. You see that here, the spin operator has a 2J component. So you want to maximize total spin, then maximize total L, and so on. Another pictorial way to think about this Houches rule is just the bus seat rule, especially relevant in periods of COVID. So, you know, if you start entering a bus, you're gonna first, you know, sit one person in every 2 seats. And then only when, so you can think of each of these seats as an orbital. And then only when these orbitals start to be all occupied, you will add an additional person with an opposite spin on the next seat. Okay. Now, given these interactions, we can go back to our little energetic exercise and go back to what is really the U effective. And this is very simple exercise, which is summarized on this slide. I do it here in a bit of a general way, in which we have a set of M orbitals. So M would be 3 for T2G. This doesn't count spin. In which we put N electrons. So N would be 1 in my strontium BO3 example. So that was 1 electron in 3 orbitals. Here it's just N electrons in M orbitals. And obviously, because of Pauli principle, N is between 0 and 2N, which is the maximum filling, so 6 for a T2G shell. And so when you do the energetics, remember, we have to evaluate the ground state configuration for N electrons and N plus 1 and N minus 1 electron. And when you do that, what you find is that the U effective, which was E of N plus 1 plus E of N minus 1 minus 2 E of N, depends on whether the shell is half-filled or not half-filled. So if the shell is not half-filled, namely if N is different from M, either larger or smaller than M, so if we have 1, 2, or 4, 5 electrons in a T2G shell, for example, you can calculate this U effective. And you'll find that it's just given, and this is essentially obvious, by the smallest of the interaction matrix elements, which is U minus 3J, U prime minus J, which is U minus 3J. What you see here is that the Houches coupling reduces the effective U enormously as compared to the bare electrostatic, not the bare electrostatic, the Hubbard screen value. But if you have a half-filled shell in contrast, so if you have 3 electrons in a T2G shell, for example, with perfect degeneracy, and you do the same mathematics, you will find that U effective is now U plus N minus 1J, okay? So the Houches coupling, or I can also write M minus 1J, so the T2G shell, that would be U plus 2J. So the Houches, the effective interaction is considerably increased by the Houches coupling. And this is because when you consider the configuration with 1 additional electron as compared to half filling, you have to populate an orbital with anti-parallel spin in the same orbital because there is no room elsewhere. So this is why there is a plus here. So this means, from this argument, that half-filled subshells are usually much more prone to being multi-insulators than non-half-filled subshells, because this effective interaction is much bigger for half-filled shells. So I wanted to show you this. Yesterday, you probably remember that I showed you a plot of the critical U for the Mott transition as a function of the filling of the shell. in a calculation that did not involve the Houches coupling. And this calculation was suggesting that the critical U is the largest for half-field shell, which is the middle of this plot. So the thing looks like this, right? But in reality, the Houches coupling is very important, and it does exactly the opposite. So the critical U for the Mott transition is actually the smallest for a half-field shell because of the Houches coupling. And if you do a more realistic calculation, so this is a calculation which is done using dynamical mean field theory for a T2G kind of system. And what you see, these black bars indicate as a function of the filling of the shell, 1, 2, 3, 4, 5, 6 electrons in a T2G shell. You see that the critical U, which is here for the Mott transition, is by far the smallest in the case of the half-field shell as compared to a non-half-field shell. Okay, so this actually can also be illustrated by this graph. What is plotted here using more refined calculations, again using dynamical mean field theory rather than just these simple arguments before, of the critical U for the Mott transition as a function of Houches coupling, this time really seriously taking into account the competition between kinetic energy and electrostatics. And so what you see is that for one electron in a T2G shell, this critical U increases as you increase J. But for 3 electrons in a T2G shell, this critical U decreases very sharply as you increase J. This is just another way to plot what I was describing before in the previous slide. So this is why actually the degeneracy, the lifting of the degeneracy of the band is very important. And somewhere here, I thought I had that somewhere, but I don't know what I did with this. Yes, here we can apply these considerations to solving the puzzle of the vanadates versus titanates. If you take the material strontium BO3, which was perfectly cubic, let's say it has half of the bandwidth, which was about 1.5 eV. It's a little less than that, but it doesn't matter. We can calculate through other types of calculations that I don't want to describe in details, typical values of J for this material. And you will conclude that for a perfectly cubic degenerate shell, you will have a critical U, which would be 8 eV. Okay? So all calculations for such a material estimate that the Hubbard U for this material from a T2G point of view is about 3 to 4 eV. So no wonder this strontium BO3 material is a metal. But now, if you go to the extreme limit, where the T2G would be completely split by these distortion effects and occupied by 1 electron, we are now in the case M equal 1 in 3 orbitals, with a bandwidth of about 1 eV, because it's a little bit reduced, as we saw before. This would only require a critical U of 3 eV, and hence would be smaller than the critical U, than the bandwidth of the larger than the bandwidth of the material. Hence, the material is an insulator. So you see that the effect of the bandwidth by itself is never going to be able to explain that you cross the Mott transition, because this 8 eV is in any case way larger than the U of this material. But when you take into account the splitting of the shell, then this is a different story, and this plays a really important role. Okay, so the whole point here that I wanted to illustrate is that there is a real value in doing more than spherical Coulomb models and introducing in the theory somewhat more realistic description of both the crystal structure and the electronic structure of the material, taking into account the distortions, the real crystal structure, and the realistic multi-orbital aspect of the material, combined with a proper treatment of correlations. And having a theoretical framework to do that is essential to not only explaining what you see, but perhaps when you're lucky, also making a few predictions. So fortunately, we now have such a theoretical framework, and this results from a combination of the kind of electronic structure methods I described before, and a more serious treatment of many-body interactions of the sort I described, using what's called dynamical mean field theory. And I'm going to use my last 15 minutes. Can I use 15 more minutes, Daryl? Something like this, 15, 20 minutes, to describe a bit more how, at least the general principles of this approach. But before I do that, I just want to show you here on this slide an application of this theoretical framework to the four materials I just described. And what you see here is you can think of it as the total density of states, but in more proper terms, this is the momentum integrated spectral function as you would measure in momentum integrated photo emission. So the total number of states available for adding and removing electrons in the system, as calculated from dynamical mean field theory using the realistic structure of each of these materials. And what you see here is that the calculations for strontium, oops, sorry about that. The calculations for strontium and for the two vanadates display clearly a metallic system with a finite density of states at the Fermi level, which again is conventionally put at 0 here, while the two calculations for the titanates clearly display a gap, with a gap which is smaller for the lanthanum than for the yttrium material. And in each of these panels, the interacting many-body density of states is compared to the non-interacting, sorry, I shouldn't say non-interacting, to the density of states coming from band structure calculations, which of course in all of these four cases predict metallic system. And you see here that there are some significant differences, even in the metallic state, between the many-body calculation and the density functional theory calculation. So let me maybe elaborate a little bit on this. So first of all, you see that here, if we focus on the, obviously those are the T2G states. If we focus on the bandwidth of the occupied part of the T2G states, the bandwidth measured, obtained from band structure calculation is this, while the one that results from this dynamical mean field calculation is reduced by about a factor of 2. So this is the effective mass reduction. This is the effective bandwidth of your quasi-particles, which is reduced by a factor of 2, as found actually in experiments, as compared to a band structure calculation. But what you also see here is that besides this reduction, there are additional features here and here that are present in the many-body calculation that gradually evolve into these peaks here, into the occupied and unoccupied states in the insulator. And I will describe a little bit later what the nature of these peaks are, but you can already guess. This is the photoemission process that amounts to remove a d electron from the d shell. So the d1 goes to d0 peak. And this is the process by which you add an electron in the d shell from d1 to d2. In the jargon of some people in the field, this is called a lower Hubbard band and an upper Hubbard band. But I think it is a lot simpler to think of it as an atomic transition. Imagine you are an atomic spectroscopist, you have a D1 atomic shell, you remove an electron that has a certain cost, and this is the so-called lower Hubbard band, while the upper Hubbard band is adding an electron in your D shell. And I'm emphasizing this because it's a much more proper language to think about atoms to describe these excitations than to think about band theory. Obviously, these features are completely absent from the band theory calculation. Okay, so in the few minutes that remain, I would like to give you some idea of how all this can be combined into a theoretical framework. And basically, the concept behind this is something I've already alluded to in the previous slide, namely that atomic physics is really important. So you need to think in terms of atomic orbitals and the electrostatics of these orbitals. And this is very different from what is done in standard condensed matter theory textbooks. If you usually, if you open a standard textbook like Ashcroft and Mermin, in chapter 1 or 2, you know that materials are made of atoms, you describe atomic positions and so on. But then in chapter 3, you introduce the notion of an electron gas thanks to the existence of block eigenstates and so on. And between chapter 3 and chapter 42, the atoms are gone, only the electron gas remains. Okay. And in contrast, what I'm trying to say here is that in materials with strong correlations, you should always keep the atoms in the description and think about local atomic physics. And I've spent a lot of time in this lecture explaining how the energetics of the atomic processes in real space influence the physics of the system. So even in metals, as the photoemission spectrum that I showed you before illustrates, the electrons sort of hesitate between being localized on short time scales, staying put on the atom, and being itinerant on long time scales. This is actually a photoemission spectrum of the material I just described to you, strontium BO3. And the photoemission spectrum is conspicuously similar to the dynamical mean field theory calculation I showed you before. And it again contains two important phenomena. One is the reduction by interactions of the quasi-particle bandwidth at low energy near Fermi level. And the other one is the creation of this satellite, which is best thought of as an atomic transition, where you remove an electron from the D shell. And in dashed here is the prediction from electronic structure, band structure theory. And you see that it misses two features. It misses the reduction by a factor of 2, and it misses entirely the Hubbard satellite. And later on, in a few minutes, I will show you a comparison between these experimental data points and the dynamical mean field calculation that I showed you before. Okay, so how can we reconcile the thinking in terms of atoms and all the beauty of Bloch theorem and so on? Well, this is precisely the goal of dynamical mean field theory. And I will skip a few slides and explain the basic concepts. So the basic concept, and obviously in the whatever 8 minutes that remain, I'm not going to have a lot of time, 8 or 10 maybe. That remain, I'm not going to have a lot of time to explain the detailed mathematics, but the concept is illustrated on this slide. So we have a solid material, piece of crystalline material, which is made of atoms, and I want to keep at the heart of the theory this notion that this material is made of atoms. I don't want to replace this problem by an electron gas. However, because we live in 2020, we cannot solve this problem exactly. This is much too complicated, and it's going to remain complicated for decades and centuries to come, despite what computers do. So we're going to have to do something of an approximation or a simplification. And the way dynamical mean field theory handles this problem is in the best tradition of mean field theory in statistical mechanics. It actually replaces this extended problem by a much more local problem, which is one atom, which exchanges electrons with a reservoir. However, the reservoir obviously is made of all the other atoms. So it replaces this problem by one atom coupled to a reservoir, but the reservoir is self-consistently related to the rest of the system. That's the general concept. So the equations of that theory are made of two main equations. One of the equations describes this part of the story, which is how my atom exchanges electrons with the reservoir, and it can be pictorially depicted in the following way. Imagine I'm following, as a function of time, the valence state in which my atom is. Imagine my atom is just a stupid Hubbard atom that can be zero, singly occupied, or doubly occupied. As I follow the system, imagine you are a spectroscopist that look, a nanoscale spectroscopist that look locally at the valence state of an atom, then the state of that atom will flip from having no electron to having one up electron, then two up-down electrons, and so on. And you write an equation, which in technical terms is called an effective action, for these histories of flips between the different valence states of that atom. So this is one part of the theory. And the other part of the theory is something that relates the reservoir here to the rest of the system. So in pictorial terms, the basic equations of the theory contain two equations. It contains an atom in an effective bath, which is coupled to the bath through a hybridization function, which is the dynamical mean field called delta of omega. You have to solve this problem of an atom in a bath. And then there is an additional equation that relates the bath to the rest of the system. And all this allows you to calculate the local Green's function of the system, which can be directly related to, say, the photoemission spectrum of the material. And more generally, for those of you who are theorists, it allows you to calculate what's called the self-energy of the system, which at this level of approximation is approximated as being energy dependent, but not spatially or momentum dependent. Okay, so let me show a couple of things that this theory has achieved. So the first thing that this theory has achieved, and this is already a very old story, which is 25 years old or so, is a proper description of how a system evolves as you crank up the strength of interactions, let's say, between a metal and a Mott insulator. And from what I described before, the system should evolve from, here I'm just plotting, say, the total density of states, should evolve from a band which is half-filled to a system in which the quasi-particle bandwidth here gradually reduces. And at the same time, the spectral weight, which is removed, is transferred to these atomic-like processes which amount to remove and add an electron on the D shell, which are called the Hubbard bands in local jargon. At some point, the quasi-particles will disappear, and the only thing that will remain in the system is a gap at low energies and two sets of excitations that are these atomic-like Hubbard band excitations. So the theory has produced a quantitative way to actually calculate these sort of things and describe this process. And if I succeed, I'm going to show you a little movie. So this is just a cartoon, but I can show you a little movie, which is an actual calculation for a simple model, which is the single band Hubbard model, in which this process is computed. So let me try to do this. Okay, let's see if this works. Yes. So can you guys see now my screen here? Okay, wonderful. So now I have to find how I'm going to start this movie. And I see. Yes, I think this is going to work. So here is a set of calculations that are all collected in a little movie in which you see interaction, which is written here, being gradually increased. You see the quasi-particle bandwidth between gradually reduced and the Hubbard bands growing. And at some point, which is coming soon, the quasi-particles completely disappear, the gaps open, and only the Hubbard bands remain. Okay, so I didn't want to leave you under the impression that I was just cheating you with just a cartoon. So that's why I wanted to show you an actual calculation. Okay, so the movie I just showed you is a very old story, and this is something that was done in the early 90s for the single band Hubbard model. But since then, many people have been working in many places in the world to actually make these techniques talk to realistic electronic structure using density functional theory. And this is this happy marriage between dynamical mean field theory and electronic structure theory. And this slide, which is a bit complicated, illustrates how the process works. And I just want to tell you briefly how the process works, and just to give you an idea. So the process basically works by making a realistic electronic structure calculation using state-of-the-art tools, for example, density functional theory plus in some approximation like LDA or GGA, and computing all the plate of spaghettis that you've seen before. Once you've done that, what you have to do is to decide on what will be your target Hilbert space to describe the problem. And that comes with all the questions I emphasized of what are the proper interactions correspondingly screened. You can use your block wave functions to construct Wannier functions that describe in local manner the set of states that you keep in your Hilbert space. And then you're going to use the form of the interaction Hamiltonian that I described before, the sort of Kanamori Hamiltonian, for example, with U prime and J, to describe your many body effects. And here comes DMFT to solve this problem. So as I explained before, DMFT itself contains a loop where you have to solve a local atom in a bath and a self-consistency condition. So this is the inner DMFT loop. At the end of this loop, you will get some self-energy and some correlation effects. This in turn will mean that the charge density of the system will have changed because, for example, you've localized the orbitals more due to strong correlations. So you have to recalculate the charge density and then redo your electronic structure calculation and converge all these two loops, the big loop over charge density and the inner loop over the DMFT many body treatment. So that's, in a cartoonesque way, how these methods work. Now, in a way that allows to not only deal with the spherical Chaos model, but actually treat a real system with its real crystal structure and its real electrons. And when you do this, you can produce this sort of plot, which is now comparing an actual DMFT calculation with electronic structure realism for strontium VO3 and calcium VO3. These are the dashed lines with a photoemission spectrum. There is a long story behind this photoemission spectrum because the early data were actually not bulk sensitive, and it took a few years and various photon energies to reach bulk sensitivity. But when all this is said and done, you see that the agreement between theory and experiment is quite remarkable. And you see the two main features I was describing before. This material is a metal, so it has quasi-particles near low energy with a bandwidth which now agree very well between theory and experiment, and that's the mass enhancement of factor of 2. And the atomic light transitions which correspond to removing an electron from the D shell, and that's this so-called lower Hubbard band. Okay, so over the past 20 years, such methods have been applied to many systems and materials. And just to finish the lecture, I can show you very briefly the famous phase diagram of nickelates that I mentioned at the beginning of yesterday's lecture a couple of times. I explained that in that family of materials, entering the insulating phase comes with a different kind of structural distortion, which is that while all octahedra are locally identical in the metallic phase, in the insulating phase, there is a breathing mode in the crystal structure that appears with two sets of octahedra on the A sites, which are somewhat swollen, and octahedra on the B sites that are somewhat compressed. And again, you can do two types of DMFT calculations for such a system. One in which you take a very large set of electronic states retaining all the nickel and oxygen states and very large values of U and J, or a massively reduced model taking into account, in that case, only two EG states. And it turns out that the physical picture that you obtain in these two languages, when you do this correctly, is the same. A pioneering paper that did calculations of the first kind, taking into account all the states for this set of materials, this paper by my friend and colleague Andy Millis, Chris Marianetti, and Huan Park. And what they pointed out is that when you enter the insulating phase with this AB breathing mode in this material, what you actually find is what they call the site-selective mode transition, in which the biggest octahedra carry a spin 1 and basically 2 electrons in the EG shell, while the compressed octahedra undergo a strong screening of this local moment by the ligand holes on the oxygen, and hence there is sort of a Mott phenomenon on the large bond octahedra, while it's more like a local screening of the spin 1 on the small bond, hence the name site-selective Mott transition. And you can reach exactly the same conclusions. That's what we did later after that paper, by adopting a more low energy description in terms of only the EG states. And I don't have too much time to describe that, but it's crucial in that case to take into account properly the additional screening of the interactions to get to that site-selective Mott picture. Okay, so I think I'm going to basically stop there. Let's see. Yes, I'm going to stop there. And basically, I hope that I've convinced you that these materials are platforms for a wealth of really interesting phenomena, that the frontier of the field is design and control, using all the tools of our materials and experimental friends. And that in parallel, there is a theoretical framework that allows to treat both the realism in a realistic way, the structure and electronic structure and chemical complexity of these materials, together with the crucial many-body interactions, and putting all this together, when one is lucky, one gets a reasonable agreement between experiment and theory, and even sometimes the ability to design or predict what some of these materials should do. Thank you very much.
Thank you, Antoine, for a great set of lectures. During your lecture, 5 of the participants had questions, so I just thought I'd go through them in the order that they were asked. And,
okay.
And if people have additional questions at the end, then raise your hand and I'll call on you. The first question came when you were introducing EG and T2G, and the question was, so this is maybe 15 minutes into your lecture, are both of the wave functions normalized to unity within the real space unit cell?
Okay, let me see. Does the question refer to the fat band construction, and when we project, was that the start? Was that, I mean, let me try to find the.
Anirudh, can you feel free to unmute yourself and clarify?
Sure. I meant the Bloch wave function and the atomic orbital wave function.
You
yes,
meant
yes.
this.
Yes, exactly.
Yes. Well, there are various ways to do that, but yes, typically you should construct a set of Wannier functions that are all normalized, and then you project your Bloch wave functions onto these normalized wave functions. You could think, if you want, of expanding the Bloch wave functions onto these wave functions. Does that answer your question more or less?
Yes, thanks.
Okay.
Okay, the next question, Antoine, was in your DFT calculations for strontium vanadate, do they take into account the spin orbit coupling?
No, spin orbit is very small for this material, and it can be taken into account, but I don't think it plays a big role in this material, as far as I know. But of course, for other materials, it's very important, like the rutinates, or of course, all the 5D transition metals.
The next question was about, I think you said Ole's, Anderson's idea about the tilt that occurs toward the rare earths of the various T2G orbitals. And the question is, how does that look from unit cell to unit cell in an anti-ferrodistortive material like strontium titanate?
I guess I'm not going to be able to answer that question off the top of my head. I would need to think more. So this is referring to this sort of thing, right? I think I'm not going to be able to answer this off the top of my head, but I can give a reference. Ole Anderson, Eva Pavarini, myself, and a bunch of other authors wrote a PRL on this family of materials. I think it's in 2003. We didn't really discuss this specific point, but there is a follow-up paper, which is huge, which has something like 70 pages, and which is published in New Journal of Physics. The authors are Eva Pavarini and Ole Anderson. And I would bet that you'll find the answer to this question in this long paper. This is Pavarini and Anderson, probably 2004, 2005.
Okay, I see more questions are coming in, which is good.
Okay.
Now this next question is, when we know that the ground state is a Mott insulator, should we still take a screened Coulomb interaction? And if so, what is it screened by?
That's an excellent question. This is a clever and interesting question. There's a bit of semantics in this question that I want to first go over. So obviously, we are used to saying, and that's correct, that insulators don't screen while metals screen. Okay. So this statement is obviously correct, but it's a statement that has to do with the low frequency, small momentum effect of screening, right? So if we look at the static effective Coulomb interaction in an insulator, well, it's gonna, decay like the Coulomb interaction in metal is gonna be screened. So you could say, well, what are you talking about when you say that the value of U is reduced by screening when we have a Mott insulator? Well, what I'm talking about is that the value of the matrix element of the Coulomb interaction of the renormalized Coulomb interaction by the dielectric permittivity, right, between whatever wave functions on site is going to be very different whether I consider an isolated atom and an atom in its solid state environment. And this, of course, is going to be true both in a metal and in an insulator. If I calculate the DD Coulomb repulsion on site in an isolated vanadium atom, it's going to be something like 20 electron volt. If I calculate this in yttrium TiO3, which is an insulator, all right, and technically doesn't have low frequency, low momentum screening, this value is nevertheless going to be 3 eV, okay, or 5 eV, and not 20 eV. So this is what I mean by screening, because this this matrix element contains transitions over all energy scales, not only the low energy scales, but all energy scales. So the transitions, the particle hole excitations that reduce the value of this matrix element are present even if that material is an insulator, because there are lots of such transitions that are above the gap. So from the point of view of the low frequency, long wavelength effective interaction, insulators don't screen. But from the point of view of the reduction between the atomic value and the actual value in the solid state, this huge reduction is present in both phases. Now, there is a more refined aspect of this question, which is, should we think that this value of the effective screen interaction is somewhat larger in the multi-insulator than in the metal? And this effect definitely should exist. It's probably small, of the order of 10% or something like this, but it's usually not taken into account in calculations, at least not in most calculations. So that was a long answer, but I don't know, did I answer more or less the question?
Igor, do you want to, are you satisfied?
Well, he's muted, so he must be satisfied.
Well, he has another question though for you, Antoine. He'd like to know, is there a parameter that tells you how accurate DMFT is for a particular system?
I'm not sure there is a parameter, but there is a systematic way to go beyond DMFT and assess the size of the corrections. So the basic assumptions in dynamical mean field theory is that the self-energy, when expressed in orbital space, and I want to emphasize that very, very strongly, when expressed in the space of orbitals, not in the space of bands, is local in space. That's the main approximation that is being done. Okay, so that approximation could be a good approximation or could be a bad approximation. And we have physical intuition that tells us when we expect this approximation to be reasonable. Physical intuition goes as follows. If there is an incipient ordering in the system that develops with a very large correlation length, then obviously we would expect strong non-local effects. So that's going to happen close to quantum critical points or at very low temperature and so on. But if we are in a regime where this correlation length for any kind of incipient ordering is small, like at high temperature or high doping or far from quantum critical points, then we expect this approximation to be good. So when we are in such a regime, we can do a dynamical mean field theory calculation, but we can also correct that calculation by including gradually longer range components of the self-energy. That's called cluster dynamical mean field theory, extensions of dynamical mean field theory, and assess whether these corrections are big or large. And we know cases where these corrections are large. For example, in the two-dimensional Hubbard model at strong coupling near half filling, these corrections are very large. And you definitely need to go beyond single-side DMFT. In many other cases, these corrections can be shown to be small, and dynamical mean field theory is very accurate. But just to finish the answer to this question, maybe I would like to show a paper in which the question was answered in a different way. If you allow me for, if you just give me a minute, I will find a paper, not a paper, but a slide presentation in which this question was addressed in a different way. Just a second.
Now, while Antoine's looking, those of you that have a question can raise your hand with the Zoom feature, and I'll just call on you in order.
Yes. So this is a piece of work which deals with strontium ruthenate, which is a material that many of you, I'm sure, know a lot about, but I haven't talked about in in this set of lectures. And this material can be studied with such exquisite precision that photo emission data based on laser sources of that quality that you see on screen can now be obtained. These are data from the lab in Geneva of Felix Barmberger and Anna Tamay. And so these data are so precise that we embarked into the following enterprise, which was to directly extract from these data electronic self-energies directly from the data without any theoretical bias of any kind, or at least with minimal theoretical bias, and then assess the degree of locality of the self-energy. And this was done in a paper whose first author is Anna Tamay, and which was published in PRX about a year and a half ago, something like this. I'm not sure I have the reference here, but let me show you the results. So the result is that if you do this by extracting a self-energy in the band associated with each band, you will see that there is a very large degree of momentum dependence. But if you actually are careful to formulate that in the orbital basis, so extracting from experiment a self-energy associated with the x, y, x, z, y, z orbital of this material, taking into account that a given quasi-particle state on the Fermi surface is actually a strongly mixed combination of these three orbitals because of strong spin orbit that mixes the orbital together, then you will find this beautiful result, which is that all this cloud of points describe different angular cuts, so different momentum cuts for the self-energy. And you will see that when you formulate things in the orbital basis, then there is clearly one self-energy which is fairly momentum independent, associated with the xz-yz orbital, and otherwise associated with the xy orbital. In other words, this means that this ansatz, which is saying that the self-energy is local in orbital basis, but acquires a strong momentum dependence because of the way each quasi-particle wave function overlaps or decomposes into the different orbitals, is actually a very accurate ansatz, as directly validated from experiment. So this is one of the few papers in which there was a direct test of the validity of the local ansatz in orbital basis, which is at the heart of DMFT. In natural material. Well, that was a long answer, but so the answer is threefold. First of all, we have some intuition for which regimes are good for this theory and when series extension is needed. The second part of the answer is that there are theoretical methods to assess the strength of these corrections. And the third part of the answer is that this can actually be sometimes tested directly from experiments.
Igor, do you have any follow-up question on that, or are you satisfied?
I'm satisfied. Thank you.
Thank you.
Can you show, though, once more the title of the paper and others?
Yes, if you give me a minute, I think I can find that paper. I can even flash it. Just give me a few seconds. And here it is. And this, I need to share my screen again. Let's see. Now
you were sharing it. You just needed to make it a little larger.
Okay, fine. So this is it. And let me make this larger if I can. Sorry. Can you see this?
Yes, thank you.
So this is the paper you see about a year and a half ago or so, in which we attempted this direct test of the locality assumption. And I was myself very surprised by this result, because strontium ruthenate has been advocated as a material with strong spin fluctuations. Although when you look at the most recent neutron data, the correlation length, even at 2 Kelvin, is really not so large at all. But, you know, by the way, this similar sort of analysis was done also for the iron-based superconductors in a paper which is quoted in this paper.
The next question, Antoine, looks like it's from an experimentalist who wants to know, in strontium vanadate that has defects in it, like strontium or oxygen vacancies, what those features would show up like in the band structure. So what the effect of strontium or oxygen vacancies is on the band structure of strontium vanadate.
Well, let me try to think a little bit before I answer. So of course there is kind of a trivial answer, which may be just that if you have some oxygen deficiency and you treat this in some sort of average way, this will more or less amount to self-doping in some sense, right? I mean, the Fermi level will not be exactly where you think it is. Now, in a more serious answer is that if you start introducing defects or vacancies, well, the system is no longer really a periodic system. So you would need to do a serious supercell calculation to assess the effect of this on the local electronic structure, at least. What else can I say? I'm not the best person to answer that question, I think. For additional consulting on the electronic structure of defects, I would advise whoever asks this question to, for example, contact, there is a guy at CCQ, Cyrus Dreyer, who is an expert at electronic structure calculation of defects. And I'm sure he would be able to answer more in detail things about electronic structure of defects and how they are calculated in DFT.
Let's move on to the next question. In consideration of the correlation mechanisms, how can we compare DFT plus U and DFT plus DMFT methods?
Yes, that is an excellent question. And I would like to, I'm going to try to answer this. So DFT plus U can be seen very clearly and very rigorously as an extreme limit of DFT plus DMFT. DFT plus U is really treating the correlation effects at the level of a static, or if you want, Hartree mean field approximation. And the theory will change the result as compared to usual DFT only if there is some sort of ordering which is produced by the effect of U and other interactions at the mean field level. So it could be magnetic ordering, could be orbital polarization, and so on. But basically, there has to be some sort of other parameter that is not present in the standard DFT calculation and which is induced by DFT plus U. So it does not need to be magnetic ordering always. It often is, but it could be some orbital polarization, you know, that differs from the one of the pure electronic structure calculation. So in phases that have long-range order, for example, magnetic long-range order, there are many aspects, not all, and we could enter into details, but that would be probably too long, but many aspects that will be similar between DFT plus U and DFT plus DMFT. And in fact, if you take the low frequency static part of the self-energy, you will be able to interpret this as the effective localized field of this mean field description of interactions that you'll get in DFT plus U. However, the challenge is to describe phases in which, for example, you have fluctuating local moments. So you are not necessarily in the ground state. Imagine you take yttrium TiO3, the Martin insulator I presented before, and you are at room temperature, right? And there you are very far from any ordering. The Curie temperature of that material is 30 Kelvin. You have fluctuating local moments. There is no magnetic ordering, no symmetry breaking of any kind. And it's not really a ground state question, but DFT plus U has nothing to say on that. It just cannot produce a calculation of that regime. And DFT plus DMFT has, as a primary goal, the question of describing such phases in which you have disordered local moments and due to the basic localization of electrons that produce the mode gap, and which do not describe the mode gap as a follow-up consequence of ordering. This description of the mode gap is obviously crazy from an energetic point of view, because you can't blame magnetic ordering for opening the mode gap when the mode gap is 1 eV and the typical exchange constant is 20 or 30 times smaller than that. So the short answer is, in ordered phases with long-range order, the two theories will often provide very similar answers. But the basic phenomena of electron localization is caricatured in DFT plus U as an ordered state, while in many cases it's not.
And there's a follow-up question, Antoine. Practically, which existing codes integrate the DMFT model?
Excellent question. So there is a bunch of resources for this. And again, perhaps the simplest would be that I show some transparency, if I can find them, some slides, sorry, if I can find them. But in a nutshell, okay, maybe I can just state it. So there are various groups over the years that have produced software packages that combine electronic structure calculations and various tools to do DMFT calculations. I can quote at least 3 or 4 of them. So starting with our own, there's been a very strong effort around Olivier Parcollet, Michel Ferrero, and others to develop something which is called TRIQS, T-R-I-Q-S. Maybe the best is to Google this and show you the web page of this software. This software package is now hosted and developed very forcefully at the Center for Computational Quantum Physics in New York. Okay, so let me share my screen again. Oh, can you see this?
Not yet, not yet. You need to share your screen.
I haven't shared my screen. Yeah, share screen. Yes, okay, so this is one example. is the one which is the workhorse in our center and group to do DMFT calculations. So this is a much more general package than just doing realistic materials with DFT plus DMFT. It's a general package for doing various sorts of many-body calculations, but in particular, it includes applications that here somewhere, you see ab initio tools, DFT tools, toolbox for ab initio calculation of correlated materials. And if you click on this, you will see here a description of this package, which contains a link to various electronic structure codes, as well as some documentation and some tutorials to explaining how to do DMFT calculations with a realistic electronic structure with simple examples, strontium 303 being the sort of a Drosophila of the field, and gamma cerium is another example, and strontium 2 ruthenium 04 is also there, and so on. That's one such package. There is another one which is available from the website of Christian Houches at Rutgers University. And there is another software suite as well, which is developed around Gabi Kotlia and co-workers at the Brookhaven National Lab. And this thing is called cont'd. And hopefully, well, cont'd, yeah, cont'd. Okay, and this is another example of a software package which is developed with the support of the Department of Energy to do DFT plus DMFT calculations. So these are at least three software packages, and there are other ones also in Vienna and so on.
Okay, then there's two related questions. First, could you please give a physical intuition of the Brinkmann-Rice phenomenon of the narrowing of the quasi-particle?
Oh, yes, that's an easy one. Well, so yeah, that one is very easy. So imagine you are, well, it's a little harder to imagine these days with COVID, but imagine in normal times that you travel in a subway at rush hours, right? Okay, so comes a subway car, which is full of people, and you're standing in the platform and you're trying to enter that subway car, right? So if that subway car is such that there is one person at every single possible place in the subway car, you're gonna have trouble entering. And people who are inside will also have trouble exiting, right? So this illustrates the fact that the Mott insulator, which is the subway car, is an incompressible state of matter. Adding an electron or removing an electron is a difficult and costly process. So that's the insulating phase. Now, imagine that the subway car is not quite fully packed, but there is still some room in there. And you want to travel, you are inside the car and you want to travel from one end of the car to the other one, right? Well, that's not gonna be so easy. You'll have to push people around, right? While if the subway car was empty, you could run from one end to the other. So this is the Brinkmann-Rice effect. This is the increase of the effective mass, or more simply described, the lowering of your effective velocity due to the interactions with the other people. That's the Brinkmann-Rice effect. It's just the fact that in a dense fluid, it's hard to move around.
And the follow-up question is, why is the height of the peak pinned when one increases U?
Excellent question. That's also a very good question. This actually is not a universally true statement. This was a particular case of the calculation I showed because the system is perfectly cubic and there is perfect degeneracy. And the reason is the following. Let me go back to one band system just to illustrate the point. So imagine I have a one band system And I'm going to do an approximation that the self-energy is only frequency dependent and not momentum dependent, right? So that's the basic assumption at the heart of the DMFT approximation. And if you make that approximation, then you see that the location of your interacting Fermi surface is now be governed by the following equation. It's going to be the location of k points such that epsilon k is equal to mu minus sigma of 0, where sigma of 0 is the value of the self-energy at 0 frequency, right? But there is something in the physics of interacting quantum systems, which is called the Luttinger theorem, that tells you that the Fermi surface volume is not changed by interactions, right? For a given electron density. So because of the equation I just mentioned, you see that the shape of the Fermi surface cannot be changed with the local self-energy because, you know, it's just a uniform change of the chemical potential. So if the shape cannot be changed and the volume cannot be changed, then this Fermi surface just cannot be changed. And hence mu minus sigma of 0 should remain equal to the non-interacting value of the Fermi energy or the chemical potential. And if you think about it for 15 seconds, you will realize that this implies that the value of the density of states at the Fermi level is pinned to its non-interacting value. And this is a reflection of the Luttinger theorem. Now, of course, this statement is no longer true, even with a local self-energy, if the different orbital in a multi-orbital system or a multi-band system, if the various components of the local self-energy do not have the same value at 0 frequency. So if the coalition effects renormalize the crystal field splitting in different ways, which they usually do, this will no longer be true because you can, of course, inflate certain Fermi surface sheets and deflate other ones, keeping the total volume constant. And hence, this will also change the value of the density of states at Fermi level for each orbital component as compared to the non-interacting value.
That's Antoine. That's all of the chat answered the questions I've seen. Does anybody else have a question they'd like to raise their hand for and ask? I have one question, Antoine. I wanted to, this puzzle of strontium vanadate to yttrium titanate, I want to make sure I understood it. When we started with strontium vanadate, the T2G had, was threefold degenerate, but it seems that the distortions in going to yttrium titanate made it no longer threefold degenerate, and having one electron and only one orbital then made it half filled.
Yes, exactly. That's in essence what I was saying.
Okay.
Of course, the splitting is not such that all the three bands are completely split from one another, right? Remember, the bandwidth is 2 eV, and that splitting is only 1/3 of an eV. But the extreme limit is exactly what you are saying. So I
learned something.
Yeah. So the point is that the lifting of orbital degeneracy by distortions is actually an even more important player than the reduction of the bandwidth. I mean, you summarized it much better than I did, but that's the key point.
Well, Antoine, I want to thank you for a great pair of lectures, I certainly learned something, and I think our participants are also very appreciative by the comments that I've seen in the chat window.
Oh, wonderful. These are the things you're not telling me. Okay.
Indeed. Things like very clear, thank you, great answers.
I want a screenshot of that. Okay.
Okay. Well, I think that's the end of the lecture.
Well, thanks to all the participants for suffering through 3 hours of lecture, and I feel relieved.
Okay, thank you, Antoine. Thank you, Daryl.